Hey, hi there. In today's video, we'll be covering the second part of descriptive statistics, where we'll be exploring the measures of variation and location. Okay, so we'll be talking about standard deviation, variance, the quantiles, right? The 25 percentile, 50 percentile, 75 percentile, and all those things. Okay, so let's first import all necessary libraries, right? And then we load the same data set which we did in the previous video. Okay. So once we have all these columns, we can easily do .describe to find out the statistical parameters along with the quantiles as well, and standard deviation. So this is measures of variation, and these are the measures of location. But please understand, standard deviation and the quantiles typically hold true for continuous distributions. So quantiles or percentiles, whatever you call them, and standard deviation, they are especially meant for continuous columns or continuous data, not for discrete data, right? Typically we do it for continuous columns. So here I've extracted the continuous columns. We know that children was not a continuous column, as you saw, that children tend to be discrete, right? But still here it has found out the mean, median, and whatever it is, right? Standard deviation as well. Why? Because it's a numerical variable. It's a numerical column. So .describe does not know what's the difference between discrete and continuous. It just understands numerical and object columns. Okay, so you as a data scientist should know, or you as a person who is trying to analyze the data should know what's the difference between discrete number and a continuous data, right? So here we'll omit the children because it's discrete. So we'll only extract the continuous columns, age, BMI, and charges. Whereas in categorical columns, I'll call this as categorical, the same name which we had used in the previous video. These are my categorical columns. So children are part of the categorical columns because it's discrete, along with the object columns, which is categorical columns. Okay. So now if I want to find out the standard deviation, right? Typically I'll do it for the continuous column. So I'm looping into the continuous column for I in continuous column. So what I'll find out, the population standard deviation, and I'll also show you how to calculate the sample standard deviation as well. Okay, so to calculate the population standard deviation, we can simply do np.std of df of I. So similarly, when we can use NumPy model to calculate the mean, and also we can calculate the mean without using the NumPy model, right? So df of, let's say say age, or let's say BMI dot mean. If I do, I'll get the mean. Also, I can write it as np.mean of df of BMI. I'll get the same value. Similarly, there's a function called std. So df of BMI dot std. If I do bracket, it will give me the standard deviation of BMI. However, I can also do np.std of df of BMI. Different ways of doing the same thing. Although you can see some difference here, right? So typically, but both of them are essentially the same. However, if I want to find out the sample standard deviation, now this is where we have to use the one without the NumPy library. Okay, because here in simple function.std, there's a parameter called DDOF, degree of freedom factor. Okay, that factor is called as DDOF. And if I specify DDOF is equal to 1, it'll give me the sample standard deviation. Okay, it'll give me the sample standard deviation. Not much difference between the sample standard deviation and the population standard deviation, right? Okay, but this is what it basically means. So this basically means that, remember when we have the formula root over x minus x bar whole square divided by n minus 1. So this was my sample standard deviation. Population standard deviation is x minus mu whole square divided by n. So this is the difference. So this 1 is basically your DDOF. If I make it 2, this will become n minus 2. Right? So here I'll use DDOF is equal to 1. And this allows me to calculate the sample standard deviation. But NumPy model cannot give us that. So we have to use the function which is used without using the NumPy library, .std, series.std. df of BMI is a series.std. Okay, clear? All right. So I've calculated the standard deviation for a population and standard deviation for if it is a sample. Okay. Use both the NumPy library and also the one without the NumPy library to calculate the sample standard deviation. So you can see here for age, there is slightly some difference between the sample standard deviation and the population standard deviation. And typically your sample standard deviation will always tend to be higher because we're dividing by a smaller value, n-1. Okay, typically sample should have a higher variance, right, compared to population. Whereas BMI, you can see there is absolutely no difference. For charges, there is some difference, right? Factor of 5. Okay. Now, how do I calculate the measures of location? Measures of variation is done, right? So this is measures of variation. I'll just mention it here as measures of variation. I'll remove this out because I've already shown it below. Can you move this out? Right? You can try it on your own. You can again write it df of BMI dot std ddof is equal to 1. Okay, or you can make it as age, more significantly different. And if I simply do without this, give me this, and I can also do np.std of df of. So once we do this, right? Okay, then we can easily go to the measures of location. So for measures of location, what I'll do, so measure of location ke liye, we can find out any percentile actually. Okay, suppose I have the NumPy library, so np dot, we have to call it from the NumPy library, np dot percentile of df of, let's say, BMI itself. Okay, and if I do say 25, it'll give me the 25th percentile, which is the value which is 26. Similarly, I can change it to 1 also. It will give me the first percentile. If I make it 99, it will give me the 99th percentile. So similarly, I can find out any percentile from this particular column. Okay. So in the loop, I'll calculate all these different quantiles for each of these columns. Right? What are the column names? The column names for continuous columns where age, BMI, and charges, right? Age, BMI, and charges. So I first calculate the Q1, the Q2, and the Q3. First quantile, second quantile, third quantile. Second quantile is also but nothing but the median, and I'll calculate all these parameters for each of the columns. And finally, I'll print it out just to show you. You see here for age, the first quantile 27, second quantile, third quantile. For charges, first quantile, second quantile, and third quantile. Right. This is for your BMI. And if you notice here, one thing which is very surprising, not surprising, but this is something which you have to, understand, that the difference between the Q1 and the Q2 is different from the difference between Q3 and Q2. So what I'm trying to say here, this is your Q1, Q2, and Q3, right? 39 minus 27 is how much? Around 12. 51 minus 39 is how much? Again, around 12. So this is where almost your distribution was, almost like a uniform distribution. That is not much for bell curve to begin with, right? Whereas if you go to BMI, again, 26, 30 minus 26 is roughly 4. 34 minus 30 is also roughly 4. So that's why the distribution was very symmetrical and bell curve. Whereas for charges, if you look at this difference, it is 5,000, but this difference is how much? 7,000. So that's why there was some skewness on the right hand side, because the difference between Q3 and Q2 was significantly higher than the difference between Q2 and Q1. But this difference was higher than this difference. That's why there's some skewness on the right hand side. So this is how you have to interpret, guys. And if you interpret in such manner, there is no stopping you. The other way where you can express quantiles is by using the graph, which is called as the box plot. So let's say sns.boxplot df of, let's say, BMI. This is my box plot. Now, if I want to check the quantiles, Q1, Q2, Q3, right? How will I do that? Very simple, sns.scatterplot of, let's say, Q1, Q2, Q3, right? Okay, let me make this directly like this. A bit of percentile. of this, comma this, comma this. So this is nothing but my BMI. This is also my BMI. And this is also my BMI, right? And I'm also going to plot it with respect to 0, 0, 0, because I don't want anything on the y-axis. I only want the data points to be plotted on the x-axis, right? Okay. So once I do that, is it showing? Okay, let me increase the size. Size is, let's say, 200. So you can see here now, some points are getting shown here. Oh, I've specified everything as 25. I have to change it to 50, right? And this also to 75. So it was overlapping each other. Now let's see. Now see, these are my quantile values. You can actually superimpose on the graph and check where is it exactly lying. So which means that this particular line, the first line of the box, represents your 25th percentile. Second one represents your 50 percentile. The third one represents your 75th percentile. Now, if you want to compare for BMI, it is 26.3, which is your first quantile, 25 percentile. See, this will indeed be around 26 point something. Second one is 30.4. So you can see this is almost 30.4. Next one is slightly less than 35. So you can see slightly less than that. So this is your Q3, Q2, and this is Q1. So midline basically tells you about the median of that particular column. Okay, minimum value and maximum value. So these are typically termed as outliers by the machine, okay, because it has its own outlier treatment or outlier finder, right? It may be based on the equation which we had, right? Q1 minus 1.5 times of IQR, or Q3 plus 1.5 times of IQR. Remember? Right? These are this is the lower threshold for outlier, and this is the higher threshold for outlier. Beyond these 2 points, all the data points will be considered as outliers. But in Python, it is not exactly this formula, but it is just some empirical formula. But ultimately, this is how it happens. Okay. But in the graph, when you try to see the distribution plot, right? If I want to plot the distribution plot of, let's say, same thing, this plot of DF of BMI. Visually, there is hardly any outlier. So we do not need to do any outlier treatment. We don't remove outliers here because it's almost fine, right? So just because we are showing dots doesn't mean that you have to remove all these dots. Please be very careful because these calculations are based on some empirical formula, right? But when you look at the graph, the distribution plot, it looks fine, right? So we do not have to do everything theoretically. It's not just always by the book. Right? We have to check multiple graphs and parameters and then come to a conclusion. Now let's plot the box plot for all the columns, just like we did for the count plot in the previous video, right? Set the figure size, loop over the continuous columns, and do the box plot, and then do plt.show. If you do not do plt.show, it will only show you the last graph. So please be very careful. It will only show you the last graph. It will create problems for you. See? Okay, in fact, it will superimpose if I'm not wrong, right? It will superimpose. So you better set the figure size if you want to, and also use plt.show so that it does not superimpose on the graphs. Okay. Okay, so these charges have huge outliers. We also already know about that. Now let us try to write a function which will calculate all the descriptive parameters of a continuous distribution along with the distribution plot. Okay, same thing, I'll do it for the categorical columns also. Okay, now let's start with the continuous column. Don't look at the function and get terrified. Okay, it's a simple function. It's just that we are calculating so many parameters, just that's why it's lengthy. Okay, there's some logic which I've written, which has made it lengthy, but this is reproducible. This is very scalable. This function, you can copy paste it in your any case study, and you can, do wonders with it. Okay, so what is this function? I've explained the function here as well. So whenever you write customized function, this is called a custom function. Why? Because this is something which you have created to serve your purpose, right? So the function name, you can give any Tom, Dick, and Harry name. I've given it as descriptive statistics of continuous data, right? And requires two parameters, data and columns. Data means data frame. Columns means the list of the columns which you want to loop over. Okay. This takes a group of variables or columns, integer and float. And this is typically for integer and float, guys. This won't hold true for object columns. And print all the descriptives along with the KDE plot. KDE plot means the kernel density estimator plot or the disk plot. There are two types of plots in CBOR. One is SNS.disk plot. There is one more plot called as SNS.KDE plot. Both of them does the same thing. In KDE plot, you won't get the histogram. In disk plot, you have the option of making KD is equal to false. So I'm using the KDE plot here so that we can also get an exposure to different types of plots available in Python. So first, I'll note down the size of the columns. So how many number of attributes are there, right? So if there are continuous columns, I think we had 3 continuous columns. So the size becomes 3. Now, what I've done here is when we use subplot, because when we simply use a for loop and plot it, the plots will come one below the other. And, it will be difficult to scroll through. It is not convenient for the user. So what we'll do is, instead of doing this, we'll try to create grids. We'll try to create grids and, reduce the size occupied, right? So if we have, so what I've done here is, if we have 4 columns, if the size is 4, then we'll try to arrange it in 2. Okay, arrange it. If the size is 4, I'll use 2 columns basically. 2 grids, 2 columns. I'll try to arrange all the 4 graphs in 2 columns. If the size is anything else, right, 1, 2, 3, 5, 7, whatever it is, we'll try to use 3 columns. No problem. Okay. All right. So if you use 3 columns, then there's one more column should come here. Then what I've done is I'll try to find the number of rows. So if I want to have a grid, if I know total number of columns is how much, so let's say it is 4. And if I have 2 columns, how many number of rows will I have? 4 divided by 2 is 2. There 2 columns hai, to 2 row honge. Very simple. If I have, say, 6 total columns, my number of columns will automatically become 3 according to the logic. So now we have 3 columns. So if I have 3 columns, how many rows will I have? So 6 divided by 3 will become 2. So there will be 2 rows and 3 columns. If I have 7 columns, let it make it more difficult. If I have 8 columns, let's say, sorry, if I have 8 total columns, yes. If I have 8 columns. Now let's say if I have 8 columns, my C will be 3 according to this logic. Okay, 3 columns, 1, 2, and 3. How many rows should I have? Right. So 8 divided by 3 is not purely divisible, right? We'll have a remainder. What is the remainder? What is the remainder? So 3 of 8, 3 2s are 6, 2 is your remainder, right? Your 2 is your remainder. So what happens if it is not purely divisible by 3? What I'll do here is I'll only extract the integer part. So integer yahan pe kya hai? 3, not the, I'll only the integer part. So this is basically your, say, 2 point something, right? 2.66, whatever it is. I'll only extract the integer, which is 2, which is nothing but the quotient. And I'll simply add 1 to it. Why? Because whatever images left behind, there are 2 images which will be left behind, right? After accommodating. So 8 agar hai, मुझे 3 में भाग करना है, तो 1, 2, and 3, right? Will it happen in 2 rows? No, because there will be still 2 figures which will be left behind. And I accommodate these 2 figures in the last column, sorry, last row, which is the 3rd row. That's why I'm adding 1 to it, another additional row. This is something which I've already explained, I believe, in the visualization video. You can go through it, but this is the logic. You can copy paste and use it in your own code. It'll help you. Next, I'm specifying the figure size of the entire grid, not just one single figure. Okay. So what I'm doing here, typically I use X, the width to be 20 everywhere. And the height will depend on how many number of rows I have, right? So I'm specifying 5 height for each row. So if I have 3 rows, I'll have 15 heights. And that is why I'm automating this way. Okay, based on number of rows, I'll have the total height of the grid. Next, I'm specifying count is equal to 1 because somewhere in the subplot I'll be I'll be increasing the count, because the way subplot works, it requires 3 arguments. plt.subplot, what are they? R comma C comma count. R is not number of rows, C is number of columns, count is nothing but you have to initiate it. Say 1, 2, 3. 1 represents the first position, the second position, third position. So here the position does not start from 0. Please understand, the position starts from 1, right? So the next figure ke liye, it will become 2, then 3, then 4, and 5, whatever it is. So whenever you specify a grid in a subplot, it's not necessary that all the grids have to be filled in. That's why even 8 columns can be 8 columns mean 8 variables, right? Can be fitted in a 3x2 3x3 matrix, right? Why? Because we have 3 rows and 3 columns. The last grid will not be filled in, it will be empty, no problem, right? That is how it basically what it means. Okay, so once we have this, so let me look over the columns or number of variables which I have. Then, so there are 2 types of things you're talking about, right? Total number of columns means the number of attributes we are going to loop over, or the variables, rather I can say continuous variables. Whereas this inside plt.subplot, this C represents the number of columns which I will be using in the grid. Okay, so be very careful. I should not be confused. I can rename this as variables if you want. So once I have this, I can loop over this, and then next I'll try to find the minimum, the maximum value, the range. Range is nothing but the maximum minus the minimum, then median, mean, standard deviation, the population standard deviation in this case, and the coefficient of variation. Coefficient of variation was standard deviation divided by mean, right? Sigma by mu into 100 will give me in terms of percentage. Okay. So then next I've also calculated here the mu plus minus 1 sigma. Remember, we had this mu plus minus 1 sigma, mu plus minus 2 sigma, just to see the spread of the data, right? So this is what I'm doing here. Next, I am rounding off to 2 decimal places the entire parameters which I've calculated above. As simple as that. And here you can see m1 is equal to this comma this. So clearly this is a tuple. That's why I'm using a list to convert each of these values to the second decimal places. Okay. Next, I'm calculating the quantile values here. And actually rounding it off to 2 decimal places at one go. Next, what I'm doing, once I've calculated all the values, next I'm doing plt.subplot r comma sigma count. So basically I'm initiating the first grid, right? The first small grid square. Then sns.kde plot data of I. So this I stands for the first column, right? The first variable, rather, I would say. Okay. And shade is equal to true, will be shading it the entire plot. And same as this plot, no difference. Next, I'm just like showed you, I'll on the graph itself, on the distribution plot itself, I'll be denoting the mean, median, mode, standard deviation, all those things, mu plus minus 1 sigma, all those quantiles as well, maximum minimum value, all these things I'm going to plot it here also. Now, how do I plot it? As soon as a scatter plot requires 2 things. What? X comma Y. X-axis mein kya hona chahiye, Y-axis mein what will be. On X-axis, I'll specify the values. On the Y-axis, I'll just make it as 0, which means that it does this value, this coordinate does not have a Y coordinate. So it will be lying on the X-axis, right? And I can specify the value, which is mean, median, whatever value I want to plot. Similarly for the mu plus minus 1 sigma. So mu one be mu minus 1 sigma, and the one be mu plus 1 sigma, right? So somewhere here or here, whatever it is. Similarly, I'll do it for Q1, Q3 because median itself represents the Q2. Q1, Q3 I'll plot, minimum, maximum I'll plot. I'll specify the label so that I can have that name in the legend. Okay, I'll specify the size of the markers and everything. I can here denote also the marker type also, circle. By default is circle, you can make it triangle and everything. Okay, so once I have that, next what I'll do is I'll specify the X label. What is the X label name? variable name, and while will be of course density because you're plotting the distribution plot. Specifying the font size as well. Okay. Why am I doing this? So that I do not have to manually write it down, because I'm already looping over the columns, right? I stands for what here? I stands for the column name, all the individual column names, all the variables, right? And of the data frame. So here I'm just doing this dot format. This is already know. This is also something you already know. String format. Dot format of I will basically put the I name within the string. Next, if I want to put a title, right, on the graph. On a title, I'm specifying everything: the median, the mean, the standard deviation. I'm using a new line character here, /n. I already mentioned, I think, the second video that \n will start again from the next line. Right. So in the first line, I'll have mean, median, standard deviation. Second line, I'll have mu plus minus sigma. And then mu plus minus sigma will be enclosed within a tuple. And coefficient of variation also in terms of percentage. Right. Then again, next line I'll have minimum, maximum value and range. And again, next line I'll have Q1, Q2, Q3. Very simple, guys. Once I have saved this entire string in title, next I can do title.format. So this string here is this, the bigger one, right? Because I have more information to put in. And then I'll do dot format with the respective values it should take. Okay, so in this brackets will be filled by the respective values of the parameters. Mean ka kya hai? Mean, this mean is string, but this bracket will be filled by the mean which I've calculated above from the data frame variable. Mean, median, standard deviation is correct. Then comma directly give this. So mu plus minus sigma, 1 sigma, whatever you call it, will have this two values in one tuple. Coefficient variation in percentage, minimum, maximum, range, and also Q1, Q2, Q3 in one tuple. Okay. Font size I mentioned. PLT.legend, and all these legends which I already have here. Remember, label means this will be coming legends, and this legend should be in the upper right corner of the graph. Now, and I'm again incrementing the count so that when we plot the next graph, which will be here, this will become 2 for the second variable. Very simple, guys. Very simple. Once I have this, okay, I think I've changed the column name, which is descriptive statistics of continuous variable. See, I beautifully get everything. Mean, median, standard deviation in first line. The second line, mu plus minus sigma and coefficient of variation. Third line, minimum, maximum, range. Fourth line, Q1, Q2, Q3 in a tuple. How difficult was it, guys? Very simple, right? So you can use this call function everywhere. No problem. Okay. Specifying the legend position, upper right corner. And here you can see the values of mean, median, quantiles, and all those things on the x-axis, because I specified deliberately that the y-axis should be 0. There's one more function which I forgot to mention, that is for sns.line plot. This is for drawing a line. So if you specify the starting index and the ending index, it will simply draw a line directly between the 2 points. Okay, and that is because M1s is already a tuple. Okay, this is already a tuple. Okay? So you can directly draw the line between these 2 points. Okay. So once I have this, I can do the same exercise for discrete data as well. So this will be discrete, or you can make it as categorical data. Okay. Or categorical. All right. So for categorical, this takes a group of variables, categorical. Okay. And plot all the count plots and the value underscore counts, right? Okay, so let's say size, again the same, the entire logic is exactly the same. Okay, this also the same way. I've used 6 height for every row. How many categorical columns were there? Cat underscore calls 4. So if it is 4, then it will be 2 cross 2. 2 columns and 2 rows because I specified it to be 2 here. So count is equal to 1, same thing. So what I've done here, what I'll do here is I will do the bar plot, count plot rather. I would plot the count plot, and with it, along with it, the proportion of the individual labels. Okay, how do I do it? df of, let's say we have children. Okay, dot value underscore counts. And if I simply do normalize, this is something which we have already done before, guys. I'll get the proportion, right? And in fact, I can round it off to 2 decimal places also. Very simple, right? So once I have this, I can just simply, denote this in my title so that people get to know. And also I'll also, specify in the graph how many unique values it has. So here we have 6 unique values, right? Length of this entire thing will give me the unique values. Or you can simply use a better way. Let's say data of calls of I dot same thing, right? Okay. Dot n unique. Yeah. All right. Let's do this. So done. Then subplot count. This is something which you can use, which you may not use, up to you. Okay. If you want to give some space in the horizontal domain, we can use a plt.subplots underscore adjust. Each space is equal to 1. We'll give some horizontal space within the 2 columns of the grid. Similarly, we have W space also. Okay. I think V space, something like that. You can check it out. If I do not do it, let's see what we get. Then once I have the subplot, but on the subplot, what I'm going to plot, I'm going to plot the count plot. So here, please understand, I'm not only just looking over the column names, I'm looking over the index of the column names because I'm using for I in range of length of calls. I can actually make it very more simple. For I in, say, let me make it as calls only. So if I make it calls, it means that I stand for the column names. So I don't have to use calls of I every now and then. Okay. My code will become less complex. Done, right? And again, that format of nu, comma, norm count, directly you can give. Here itself, you can do dot round off to. Clear? Okay, so once I have this, let's see if this works. It should be categorical columns. Cat underscore calls is what we had used before. List decimal strings or slices, not integers. Okay. Oh, this again. Let's make it simpler. Understood, right? Earlier I was looking over the indexes of the column names. Here I'm looking over just over the column names directly. You can see here. You can see here that this portion, right, is overlapping because of the title is pretty big here. The entire title, I'm specifying how many unique values are there, also the proportion of the individual labels, right? So in that case, you can basically you can adjust the space. You can see here height. So H is not the horizontal spacing, but the height. Okay, please be very careful. Similarly, we have W space for the width. This is for width, and H space is for height. All right, so this is what you can use. So once I increase the height, I can easily see the title properly. Okay, you may remove this name entity everywhere actually, but it's fine if you keep it. If you want to remove it, you can do it because the entire norm count here is nothing but a string actually, because you're putting it inside quotes. So you can simply dot split off name of 0. That's up to you. Okay. All right. So basically what I'm trying to say here is See, it is gone, right? So that's up to you, like how you can present it. If you want to remove it out, you can remove it out, no problem. It's up to you. Okay. And you can see here the unique values of sex is 2, male and female. Here, smokers also yes and no. This is also region, which is 4 unique values. Here they have 6 unique values of children, where 0 accounts, people with no children accounts for the maximum proportion, which is 43% of the data actually do not have children. 27% of the data belong to the Southeast region. And the number of non-smokers is more, 80%. Number of males accounts for 51% of the data. And see 51 and 49%, there is not much difference. Here it is 80 and 20, there's a huge difference between the two, right? This is how you can actually understand. And you can see as the number of children increases, the proportion also decreases in that fashion, right? Okay. All right. So this is all for today, guys. Hope you enjoyed it. I hope you're learning a lot. And this is going to probably open your eyes to how we can implement statistical parameters, how you can calculate statistical parameters in Python, and it will slowly try to bridge the gap within visualization and statistics. So we used both things here. We are in the process of us implementing statistical methods. We are also revising visualization and trying to, plot the dots. I hope this was helpful for you. Keep practicing. See you in the next video.